Good morning. Here yet again for another lovely session of CENG 3325 Structural Analysis. This is going to be the 15th lecture in the video series, and today we're going to be finishing up with our look at beam deflection. So first, I want to look at deflection with discontinuities. I want to consider how we can handle a beam that is undergoing under load, under transverse loading, and how we can find the deflection along the beam if there are discontinuities. So, deflection with discontinuities. So deflection with discontinuities. So previously, we have looked at one or two examples of deflection, and this has always been with things that had no discontinuities in the loading. In other words, we had something like this. You might have a simply supported beam, for example, and some load function, some sort of varying load, arbitrary load function, etc. But as long as this function is continuous, there are no discontinuities within the load function, and you can integrate it and find the deflection via one single zone of analysis. But what I would like to look at instead is something more complex, something of the type of discontinuities that we discussed when we were looking in depth at shear and moment diagrams. So, first of all, I'd like to do a bit of review on boundary conditions. Let's review boundary conditions. And the difference between pin and fixed supports. So you can have, if you have a, and this is a review from last time, but if we have a pin or a roller, and a fixed support, so let's consider this here. This is going to show, I'm going to draw each support and its original shape and then its deflected shape. And a fixed support would look something like this initially. And upon each, I will apply a load P, or just some arbitrary transverse loading. So when I do this, what happens to the shape of each? Well, a pin joint, of course, is unable to resist bending or unable to resist rotation, so it's just going to bend downward like this. The end is actually going to rotate. The fixed support, however, is going to be able to resist rotation, so its deflected shape is going to look something kind of like this, or maybe more like this. Initially it's joined up very firmly with the support. It's not rotating at all. But then it starts to droop down as it gets closer to the applied load. So in other words, though, what does this mean? Here we have a theta. Even right at the support, there will be a certain curvature theta, or certain slope theta. And then, of course, we do have y, the deflection, equal to 0 at the end. But for the fixed support, y is equal to 0, but theta is also equal to 0. So this produces our boundary condition table. From this, we can produce a boundary condition table. Theta and y for a pin, well, pin/roller and fixed. For a pin or roller, theta is not equal to 0, so we don't really know anything. That's not really a boundary condition we can use. But we do know that at the end, that at a pin, the y, or the deflection, is equal to 0. But for a fixed, both the theta, both the slope and the deflection, are both equal to 0. And we're going to use this to solve an example problem. Okay. So let's look at another example. And let's consider this here. This is going to be a little bit more complex. So let's say we have a cantilevered beam, and this one I'm going to put some discontinuities in. So I'm going to go ahead and show the beam, including its reactions, because I think that's something by now that you can easily solve for, fairly trivial. The loads here, I'm going to have first a distributed load. This one may look familiar. A distributed load of 2 kips per foot. Then a downward point load of 10 kips at the end of the distributed load. So we're going to keep things relatively simple by having only one discontinuity point here. 10 kips, then we're going to have a 40 kip foot moment at the end, or a couple at the end. And then reactions at A, MA will be equal to 136 kip feet, and AY, the vertical reaction force at A, will be equal to 22 kips. And then the dimensions, it's going to be 6 feet from here to here, and 4 feet from basically the distributed load region will be 6 feet long, and the unloaded end will be 4 feet long. So again, this may look familiar. I believe we worked through an example with this previously, finding the shear and moment functions. So this is going to be, this here is going to be 6 foot and 4 foot. And looking at this, how many discontinuities do we have? Or where do we have discontinuities? We have discontinuities at A, B, and C. The discontinuities at A are basically the end of the beam and all of its loads and all of its reactions. The discontinuity at C is the moment and all of the moment and all of the on the end of the beam itself. And then the discontinuities at B are the end of the distributed load and the point load. So basically what we need to do is we need to divide this into 2 different zones of integration. And so we're going to have a distributed load here at X, or it's not distributed load, sorry, one zone of analysis, a cut here, somewhere in the first 6 feet, and then another cut here in the second, in the last 4 feet. So we'll have 2 different X's that we're cutting at here. And so we have all this, and we want to develop the deflection equation. Develop the deflection equation. Okay, so I'm just going to go ahead and give us the moment function for brevity's sake. I think by now you know how to get the moment function. This should hopefully be fairly straightforward. The first step would be to get the reactions, which you already have. The second step would be to get the load function. The third step would be to get the shear function. And the fourth step, well, no, not a function. And the fourth step would be to get the moment function. And we could do this either via integration or the method of sections, any way you want. Actually, method of sections would probably be the easiest here. But again, I think you know how to do this by now, so I'm not going to belabor the point and spend a lot of time on it. I'm just going to tell us that the moment function that we get, and I believe I may have worked through this one in a previous video as well. So the moment function here is going to be 22x minus x squared minus 136 when x is less than or equal to 6 feet. And then the moment function is going to be equal to negative 40 when x is greater than or equal to 6 feet. Greater than or equal to 6 feet. So we now have our moment function. I want to use these. Again, I don't want to spend too much time getting something we already know how to get. So I want to jump straight to finding the y and the theta function and the y function. Okay, so I am going to refer to this as region 1, and this is region 2. So just like I might have a y1, just like I had a moment 1 and moment 2, that sort of thing, I'm going to have a theta 1 and a theta 2, a y1 and a y2. Okay. So we want to find theta as a function of x and y as a function of x. and y as a function of x. Okay, so let's first look at for x is less than or equal to 6 feet. Let's do the first region first. Okay. So we have the formula that we developed previously, that theta as a function of x is equal to the integral of moment divided by EI. Or I could say that theta 1 as a function of x is equal to the integral of m of x over EI dx, which will be equal to 1 over EI. And we're just going to do this integral in terms of EI. So 1 over EI times the integral of 22 minus that, or 22x minus x squared minus 136 dx. And if you work through that integral, you will find that this is 1 over EI. Again, that's just a constant of integration. That's not going to change. Times 11x squared minus x to the third over 3 minus 136x plus c1, a constant from the integration. So we will come back to this. I'm going to call that just 1 for now. And then, let's see. Let's get this. Actually, let me just go ahead and get the boundary condition now. We do need a boundary condition to solve for this C1. And the boundary condition is the following. Well, we know that because this is a fixed support, this is a cantilevered beam with a fixed support at the end, so therefore we know that theta at x equals 0 is equal to 0. So therefore, we can plug this in here and basically say 0 equals 1 over EI times 11 times 0 squared minus 0 to the third power over 3 minus 136 times 0 plus C1, which is just a very elaborate way of saying that C1 is equal to 0. So C1 is clearly equal to 0. So theta 1 as a function of x, our final theta function, is going to be equal to, is simply going to be equal to, that will be, let's see, that's going to be simply 11x squared minus x to the third over 3 minus 136x plus, well, just plus 0, so just minus 136x. And so, oh, and of course times 1 over EI. Can't forget the 1 over EI. And that is our, the equation for the slope of our beam as a function of x in the first 6 feet. Questions on that? Really just a straightforward integration and implying a boundary condition. Okay. Any questions on that? Okay. Next, y1 as a function of x is simply going to be the integral of theta 1 as a function of x dx. And so that's going to be 1 over EI times the integral of 11x squared, let's see, 11x squared minus x to the third over 3 minus 136x, or minus 136x, and then plus, or just times dx. And the integral of that is going to be, let's see, that's going to come to, 1 over EI times 11 over 3, 1 over EI, times 11 over 3 x to the third, minus x to the fourth over 12, minus 68x squared, and then here, plus C2. Okay, so, and we do need a boundary condition here. And the boundary condition, again, because this is a cantilevered beam with a fixed support at the end, we know that y, the deflection at x equals 0, is simply going to be equal to 0. And that can very clearly lead us to that C2 is equal to 0. So therefore, y1 as a function of x is simply going to be equal to 1 over EI times 11 over 3, or 11 thirds x to the third, minus x to the fourth over 12, minus 68x squared, and just that, no C2. Okay. Now that was fairly straightforward, but on the next one, for the next region, I want to illustrate the idea of carrying through your constant to the next layer of integration. Mm-hmm.
Let me say it was canceling for beam, and just like the y and the theta were 0 at, say, a pin. Yeah, at a pin, y was 0, yes, but for theta wasn't 0 at a pin or roller.
Yes, if you have a pin or a roller, the theta would not be equal to 0. This is a fixed support, though. It's a cantilevered beam with a fixed support, so therefore y is equal to 0. But yes, if we had a simply supported beam, we would have to work through the equations all the way through, and then apply systems of equations to solve for the constants. Okay, or you have to solve simultaneous equations. Okay, so next I want to work with the case where x is greater than 6 feet. So let's keep at this. For x is greater than or equal to 6 feet. So again, here, we know that theta 2 as a function of x here. Theta 2 as a function of x is equal to the 1 over ei times the integral of m of x dx, which will be equal to 1 over ei times the moment function, the integral of the moment function, which is simply negative 40 dx. And this will come then to 1 over ei times negative 40 plus what I'm going to call C3. Negative 40 plus C3, just a constant. And I'm going to leave that as like the... Oh yes, one of those things. That's how integration works. Negative 40x. It's nice if I don't leave off the x. Plus C3. And that's theta 2 as a function of x. Theta 2 is a function of x. Or the slope of the beam as a function of x. And I'm going to go ahead and get the y2 right now. At least its general form. y2 as a function of x is going to be equal to the integral of theta 2 as a function of x dx, which will equal 1 over ei, and that's going to be equal to negative 20 x squared plus c3x plus c4. Plus c4. Okay. So notice I just kept carrying through the integration, and we're going to do this because it's going to be a little bit tricky to solve for this because we're going to need to use boundary conditions, and neither of them is going to immediately equal to 0, but we'll see. You'll see what we're referring to here. Okay. So first thing I'm going to do is I do have two equations here, and I'm going to solve for I want to solve for C3 and C4. C3 can be solved for just using the boundary condition at the jump point, at the break point essentially. And the boundary condition, just like we did when we worked with moment functions, when you have discontinuities, often the moment will continue through, often the deflection will continue through, those sorts of things. And the boundary condition here is that theta 1 at x equals 6 must be equal to theta 2 at x equals 6. Looking back at this beam, there's nothing actually for any beam essentially, that as long as a beam, the only way a beam would not have continuous curvature is if it's suddenly a change in cross section or something like that. That's the only way it wouldn't work, or if there was a literal pin that this thing could literally twist on or something like that. It wouldn't even be one beam at that point. As long as something is a single beam, the deflection and the rotation are always going to be continuous across the entire beam. The moment and shear won't be, but the thetas and y's always will be. Okay, so let's find this. And theta 2 at x equals 6, if I substitute in 6 into my previous expression, I will get negative 492 over ei. Actually, let me go ahead and show that. Let me just do it right and proper. So that's going to be 1 over ei So let's get that, times 11 times 6 to the squared minus 6 to the third over 3. I can manage to write properly. Minus 6 to the third over 3 minus 136 times 6. 136 times 6. Just simple substitution. And that is equal to 1 over EI. That's the deflection at, basically that I want to put in the expression at x equals 6 for theta 2. 1 over EI times negative 40 times 6 plus C3. And interestingly enough, the EI is going to cancel out. And if you go and solve that for C3, you will find that C3 is equal to negative 252. C3 is equal to negative 252. Okay, so that gives us a final theta 2 as a function of x is equal to 1 over EI times negative 40x minus 252. Okay, now let's do the same for the y. So we now have our equation for theta, which again is the slope as a function of x. And so now we want to do the same thing for the deflection. So we're going to do a boundary condition. And the boundary condition is that y1 at x equals 6 is equal to y2 at x equals 6. And again, we're assuming that the beam is, basically we're assuming a continuous beam. So y2 at x equals 6, we're just putting in our, again, I'll set up the same kind of thing. So 1 over EI times 11 thirds, 6 to the third power. 11 thirds times 6 to the third power, minus 6 to the fourth over 12, minus 68 times 6 squared, is equal to 1 over EI times, this is basically, I'm using the expression for y2 that we already got, 20 times 6 squared, minus 252. This was not in the original expression. This is the C3 that we got earlier. Minus 252 times 6, plus C4. And again, the EI cancels out. And if you solve this for C4, you will find that C4 is equal to 468. And C4 is equal to 468. So let's get our final equation. Let's summarize this with a final equation. And that is that y is a function of x is equal to the integral of 1 over EI. And I'll just give the final, we were really after the deflection equation, so I'll just list this here, summarize this. 1 over EI times 11 thirds x to the third, or 11 thirds times x to the third minus x to the fourth over 12, minus 68x squared when x is less than or equal to 6. And then 1 over EI times negative 20x squared minus 252x minus 252x plus 468 when x is greater than or equal to 6. Okay. Next, I would like to provide a brief example on how you actually apply this. So I'll give us one final challenge on this problem. Find deflection. Let's find the deflection. Let's find y at x equals 10, basically the end of the beam, for a W, let's do W 12 by 14 steel beam. So previously I've done all of this in terms of just blanket EI. However, that's always been a little tricky. Not always been a little tricky, but in the sense that I've always been glossing over how we actually handle this EI. So let's do this. I think I can squeeze it into this slide. I think I can make that work. So the key to this is that we're going to have to consider units very carefully. So first let's get the function. Y2 if we just plug and chug here at 10, EI, 1 over EI times negative 20 times 10 squared minus 252 times 10 plus 468. And if you throw that all into a calculator, you will get negative 4,052 over EI. Now the question is the question I have, is this a unitless expression here? Yeah, I mean, I've been kind of lazy working through these. Like, I haven't listed units, but if I really wanted to be right and proper, I probably should have like kips in there and some units in there. But we've just been operating under the expression or the understanding that this is in kip feet. So kips and feet are baked into that number. This is not a unitless expression. Now you can do. There are sometimes you can do calculations that are unitless, and then you just work through them that way. But as we've done this is not a unitless expression. So, in other words, when we're putting in our properties, we need to use compatible units, or we have two ways of doing this. One, we can either convert this to something else, to the units we want, or when we're putting in EI, we can convert this to the units that we already have. And I think that's what we're going to do here. So we have our expression, but all we really have to do is substitute in E and I. But the problem is these are going to be in slightly different units for what we're used to, or to what we've been using. So for example, what is the modulus of elasticity of steel? 29,000 KSI. That's what you always remember, hopefully. At least all my US students will remember that, but anyone watching this over in metric land, or also known as the rest of the world, can use, well, you have to memorize something in megapascals or gigapascals. But anyway, here in America, we use 29,000 KSI. So, anyway, 29,000 KSI. And so I'm going to have to use a very odd unit for modulus elasticity that we're not used to using. And that is kips per square foot instead of kips per square inch. Something kind of odd, but that's not really that difficult to convert. All you need to do is multiply by, because this is basically, again, let me write this so we can see how to do this, as kips over inches squared. So to go back to go to kips per foot squared, or K, let's see, instead of kip, KSI would be KSF, I suppose. You would have to multiply by 12 inches over 1 foot quantity squared, and that will give us 4,176,000 KSF, kips per square feet. And I, similarly, the moment of inertia, I got this from looking this up in the AISC steel manual. And this is 88.6, the moment of inertia of it in the strong axis is 88.6 inches to the 4th power. But then we want to multiply that by, let's see, that's going to be 1 foot over 12 inches to the 4th power. And we have a moment of inertia of a very ungainly unit, or number, of 4.27 times 10 to the negative 3 foot to the 4th power.
Why did it change from 4.17?
Oh, E and I, yes, okay, yes, two different things. This did not convert to this. This is just two different, two quantities. Okay, so then y as a function of x, I can get, or y at x equals 10. Now it is just plugging and chugging. Negative 4,052 divided by 4176 000, huh?
Was x at 10?
Oh, x equals 10, yes, thank you. X equals 0 would be quite boring. It'd just be 0. Then times, so basically 4.1 million times, much smaller, 4.27 times 10 to the negative 3. And we will get a final reasonable deflection of negative 0.227, and we know this will be in feet because that's our units here. Negative 0.227 feet downward, or converting to inches, this would be equal to negative 2.27 inches. Wait, that doesn't quite make sense. Negative 2.27 feet. Okay. something fishy about my numbers here. Let me double check that. Just a second. 2.72. Yeah, okay, that makes more sense. Wait, it's 2.72 feet?
No, 2.72 inches.
Okay, that makes more sense, yeah. And there's a slight error in my notes here. Negative 2.72 inches. Okay. And usually I like reporting deflections in inches. That's usually more convenient for most civil engineering applications. So I'll go ahead and box that and report that as my final answer. All right, so questions on this. Questions on this. Basically, I hope this is fairly straightforward. What we did was we just worked through finding the rotation function or the curvature function or the, well, I got to be careful with my language. Sometimes I say curvature and rotation and slope interchangeably. As we saw last time, they are different things. But we found the slope function. Theta is a function of x. Then we found the deflection equation, and then finally we we applied appropriate boundary conditions, and finally we applied that at a certain point. Okay.
You can say.
Huh?
Can you explain the boundary condition for theta 2?
The boundary condition for theta 2. Okay, so the question is, can we explain boundary condition for theta 2? Absolutely. Oh, missed a slide there. Okay, anyway, the boundary condition for theta 2 is basically that, you know what, maybe I can explain it over here a bit better. I'll draw it out. So boundary conditions. Again, with discontinuities, or at a discontinuity. So let us say you have a beam, and you have some sort of loading on it. Now, the load is what's going to cause the discontinuity, right? The load is what's going to cause the discontinuity. And there may be other loads as well. But you can end up with some arbitrary deflected shape. I don't know, you could end up with some, depending on the loading. Again, this loading would not produce this, but you might end up with some really weird deflected shape, something like this. But the thing about this is that while W of x, V of x, and M of x can have discontinuities, Or I shouldn't say discontinuities, can have jumps. In other words, like I can make, for example, moment can jump when I apply a couple, right? Your moment function, your moment diagram can jump when you apply a couple. Moment function jumps at a couple. So if I have a beam, for example, and I apply a couple to it like this, the moment function might do something, let's see, that would cause it to increase. The moment function would do something like that. So the moment function might do something like this, like there, okay? So that is, again, my moment function, or a couple can cause the moment function to jump. Or a shear function can also jump. Or shear function can jump. Or it jumps at a point load. So if you have a point load, this is your actual beam, you have a point load, well, your shear function would look something like this. This is your zero line. Maybe your shear function comes along and goes like this. It drops. Those are sharp jumps in the shear and moment function. Now, theta and x and y of x can have discontinuities, but they will not have sharp jumps. But not sharp jumps. Because they're actually describing the physical curvature of the beam. So for example, the only way to get what would a y jump look like? Well, you would have to have, for example, a jump in y. Let's think about a physical beam. It would have to look, the only way that would work is if you literally had a sharp jump in the physical beam. So it would have to look something like this here, where the centroid just immediately jumped for somehow. This is what a jump in the y function would look like. And that doesn't happen. The moment function can jump, but that's not going to result in a sharp jump in the actual geometry of the beam. Or a jump in theta as a function of x. The beam would look, a physical beam would look something like this.
I guess what I'm asking is, there have a discontinuity. Those are two different integration zones.
Yes.
Like say, for that one, let's say it was at x is equal to 6. You're saying at that point, both integration zone 1 and 2 at 6, they will have the same.
Exactly. Yes, we're saying that both integration zones will have the same value, because this is what sharp jumps would look like. If we didn't have that, we'd have to have something like this. This would be a sharp jump in theta as a function of x, where the beam was coming along and then just immediately changed direction. That would be a jump in theta as a function of x. So I'm just trying to distinguish in your all's minds the difference between jumps and discontinuities. Discontinuities are fine, jumps are not in theta as a function of x and y as a function of x. A discontinuity, so in terms of functions, discontinuities look like this. In theta of x would look something like this. If you have your theta function, it would look something like this. If this is your, it could look something like this. This kind of thing. Maybe with this being the 0 axis.
Would you draw diagrams for deflection?
The question is, would we draw diagrams? Sometimes you can, especially deflection more than the slope. But notice here, we have several discontinuities. We have 1, 2, I guess 3 and 4 discontinuities here. But in each of these cases, even though we have discontinuities, we don't have jumps. Because again, if we're actually going to have a jump in the theta function, our physical beam would look something really weird like this. Same thing with as y as a function of x. If you have you can have discontinuities, you can do anything you want in terms of discontinuities, but you should be able to draw the y as a function of x without lifting your pen, essentially. So maybe this is the 0 line. There are many discontinuities in this function, but it is still continuous. So if we were to go back to calculus, we would say this function is continuous but not differentiable. Remember that way back in calculus? This is a continuous but not differentiable function, because the limit from the left equals the limit from the right, et cetera, et cetera. So again, back to the boundary conditions. Interior boundary conditions, essentially. Again, because y as a function of x, or theta as a function of x, and y as a function of x are always continuous, you can always use the end values of one zone of integration as the boundary condition for the next. Okay. Let's see here. All right, and I think that'll do it. Okay. So any questions on this? Any other questions?
So a pin connection would be the same as a pin support?
Yes, a pin connection would be the same
But
as,
it has zero moment on a pin connection.
Exactly,
so it
yes.
has zero deflection, but it has a different slope though? It'll have not a,
oh, okay, that's
Not
another,
zero
that's
slope.
another, are you talking like an internal pin?
mm,
Okay, an internal pin will not necessarily have zero deflection.
okay.
It not, will not, it's because it's not actually supported at that point, but it would release the moment at that point.
Okay.
Okay? Other questions? Okay, all right, that'll do it for today. Thank you for watching. I hope you all enjoyed this. Hope you learned a few things. I'll see you all next time, and as always, thank you.